I just press continue.
No timer. Another couple minutes there. I see more people are starting to join in.
Yep.
Okay, well, it's 1 o'clock there, so we'll get started, and people can continue to join in. Good afternoon, everyone. To start our webinar, I'd like to introduce our speaker. Dr. Tingley has worked in the wood products industry for over 40 years. He received his Bachelor of Science in Forest Engineering and Master of Science in Civil Engineering from the University of New Brunswick. He completed his Ph.D. at Oregon State University in Wood Science Technology and Civil Engineering. Dr. Tingley currently holds more than 40 published patents in the reinforced wood field in the US and other countries. He has authored over 125 conference proceedings, publications, and articles in the area of reinforcement of wood and wood composites. Dr. Tingley is the Senior Engineer for Wood Research and Development. Dr. Tingley is currently the Chairman of the Subcommittee on the Development of the Handbook of Conventional Maintenance Practices for Railway Bridges for Committee 10, Bridge Maintenance and Construction, and he also serves Chairman of the Subcommittee on Specifications for Committee 7, Timber Structures. So just before we get started, Dan, I'll pass it up to you. For all the attendees, we'll hold all the questions off till the end. And at that time, you'll see a raise hand option down below. And then if you have any questions, I'll allow you to speak and you can directly ask your question to Dan. Or if you prefer, or maybe you don't have a mic, you can always type it in the Q&A section and I can read it to Dan myself at the end of the presentation. So with that, Dan, I will pass it over to you and we can get started.
Well, thanks a lot, Dave. It's good to be back again and visit with you folks. I can remember the 3 webinars we held a while back, and it was an exciting time, and it was great to get together with folks and talk about timber bridges. And so I'm looking forward to this 3-part series where we're going to move a little bit further down the road and get into more of the details about timber bridge design and timber bridge utilization, inspection, restoration. And I hope that this provokes more interest in timber bridges. That's why I do these seminars. It's my passion to develop and improve the utilization of timber bridges today around the world. And so I'm looking forward to this first part today, which will kind of set up the fundamentals of how timber is an anisotropic material, meaning different properties in different directions, and how its characteristics and mechanical properties then impact the design and utilization of the bridge, from everything from inspection to maintenance, restoration, design, and then of course the construction of greenfield projects, brand new timber bridges. And so next week we'll roll into part 2, which is kind of getting into some interesting topics like wood welding. And you might think, how does one weld wood? You don't use welding rods for sure. And we're going to talk about that in a little bit more detail, and that'll be interesting for you. And then of course over into part 3, where we talk about joining wood and connectors, where out of sight doesn't mean out of mind. And so that's kind of a little synopsis of our 3-part series. And with that, we're going to kind of move on. As I said, this first webinar is about the wood physical and mechanical characteristics that impact how we utilize timber bridges today, how we look after them, how we maintain them. And just to remind us about some of the advantages of timber bridges that we talked about in the early going of the last 3 seminar series, we remember some very important points, things like the fact that a timber bridge is 1/8 the dead weight of an equivalent load capacity concrete bridge. And this allows smaller substructures and subsequent savings to occur because of it. Longer spans can occur because the self-weight doesn't become the single biggest design criteria like concrete. It allows reduced transportation cost because the system itself is lightweight and providing great strength to weight ratios. And it reduces the amount of heavy equipment on site. The crane sizes can be less, and the site preparation works and cost can be less. This also leads to another point, and that is rapid installation. When we fabricate the components off-site, for example, in greenfield construction, where we're machining and developing and assembling the bridge prior to treatment, that means that when we take it apart, letter and number it, send it out for treatment, make sure the treatment is right, send it to the site, the components can be, in a sense, put together much more quickly, and on-site times are reduced. And this is a big factor, particularly where you have short building seasons, environmental issues like rivers that can't be worked over or in during certain times of the year. So these things are important. It's important when you think about working during the winter, when you have to charge up concrete with plasticizers. With wood, you don't face those sorts of things. It's important with when you think about paving a bridge, you certainly don't turn on vibratory rollers to pave and get good consolidation on a freshly minted concrete bridge. You can with timber. So these things all improve the installation characteristics and the speed with which you can do it. This is a bridge here in Brisbane, Australia that I designed. It's a 2-lane bridge with a 2-meter wide sidewalk where everything is assembled on this bridge, and the whole assembled 10-meter section drops into the cantilever clips in this bridge with one lift. The crane operator for this job shared with us that the previous week he had lifted a precast concrete girder for the same span, one single girder, that weighed more than the entire assembled segment they're lifting there. And that's significant. Why is it significant? Well, the substructure in this picture was restored and reutilized to build a new bridge on it that carries heavy truck traffic, and we didn't need to replace the sub. Well, what does that mean? Less time, extension of life, less cost, improvement of utilization. And these are important features today as we look at reducing infrastructure cost and extending the life of our assets. And another factor that really plays with this is the low initial cost. Timber structures are traditionally lower in cost. We're going to see pictures later on in this presentation of a 35-meter clear span bridge called Dillman's Bridge down close to Halifax. It's currently under construction. Well, the cost of that bridge in concrete was a significant amount more, some 2 or 3-fold. So low initial cost becomes a very big factor when we're talking about timber. The traditional mode of concrete and steel has been to prove that they last longer, that their maintenance costs are lower, that we should use steel and concrete and exclude timber from our tender specifications, because steel and concrete get the job done and wood doesn't. Well, that's simply phrase. And I hope you all know what phrase is. The reality of the score on that one is that timber deserves to have a rightful position with steel and concrete in all tenders. When you take out one material, what happens to the price of the other two? They go up. And so by bringing timber into the equation with its lightweight, long-term longevity system that it brings to the table, then that improves the cost picture for bridge owners. So the initial cost then is a big factor, and timber helps reduce those costs. And I'm going to be talking about cost as you see pictures coming in this presentation. So just make a mental note of actual cost that I share with you from tender docs, and you'll see what I mean. Reduced carbon emissions are big time issues these days. You know, governments are looking to tax people for carbon. They want to find solutions that sequester carbon and bring net negative carbon emissions to play. And so as our governments look at bridges from a carbon lens point of view, they're going to move toward timber. The negative gain with the timber is significant as we look at reducing carbon emissions. And so that's a big part of it to play. You know, timber bridges traditionally takes 22 times less energy than steel and 16 times less energy than concrete. And by removing CO2 from the atmosphere through photosynthesis, trees sequester carbon and put oxygen back into the environment. Wood is just the logical choice for timber for bridges. You know, wood also has factors like chemical resistance. You know, in Nova Scotia, we don't allow the use of rust-resistant steel because we know that a patina of dew or water on the surface of rust-resistant steel that has salt inladen with it means that it will reduce its longevity, not improve it. And so in Nova Scotia, many parts of Nova Scotia and some of New Brunswick, the southeast portion of New Brunswick, we're in the highest, what we would call embedded and exposed corrosion zones in the country. Not nice places to build steel stuff. Wood has a natural resistance to these. For example, we put salt on the road. Salt is a natural preservative for wood. It doesn't lead to corrosion of wood. Wood doesn't rust. I often hear people saying they look at a rust stain on a wood bridge from a piece of metal and they say, look, the wood is rusting. Wood doesn't rust. It might have ferric ion degradation from untreated steel connectors, which leads to an embrittlement of the lignin, but it doesn't rust. Wood is with great advantages in cold climates. It doesn't shrink and expand with thermal change to near the effect of steel. Steel's coefficient of thermal expansion is 3 times timber. And of course, as we've said, in these coastal environments, wood has such great chemical resistance. Fatigue resistance, you know, wood doesn't need a dynamic factor like steel, an impact factor. Wood responds very well to impact loads. And one of the characteristics about wood that causes this is its low MOE, modulus of elasticity, compared to the modulus elasticity of steel, for example. You know, wood might be, let's say, 12,000 MPa, and steel might be 200,000 MPa. But the fact of the matter is because wood is soft and lower MOE, it shares load. It handles fatigue load better. It handles dynamic load better and impact load better. And these are positive characteristics of wood. It shares load better. That's why we say wood is forgiving. We get an old timber bridge where we got a bad actor in it, maybe 9 or 10 bad actors. It's still carrying load when a concrete bridge in the same shape would not carry the load. So wood is forgiving and has great resistance to freeze-thaw cycles. That's another characteristic of wood as well. So governments are struggling to deal with an aging inventory of timber bridges. 269,000 roughly timber bridges in North America of about 910,000 total bridges in inventory. That's a big percentage, well over 25%. And a lot of these timber bridges are in rural areas. They're not in the urban areas where they've been switched out for concrete or on our major highways. If you drive one end of Canada to the other, you're not going to go under a timber bridge anywhere. Well, that's not right. That's not the way it was at the turn of the century. In 1900, over 80% of our bridges being built were timber. And then comes the 50s and 60s, and I called it the great era or panacea of reinforced concrete, where the concrete people convinced the owners of bridges that, hey, look, that concrete sidewalk doesn't decay. And look at all those timber bridges you got that are decaying and they don't last because of poor maintenance strategies, and they convinced governments that concrete bridges would last longer. Well, that great panacea has come to an end because we've witnessed concrete bridges blowing up at 40 years. The biggest infrastructure disaster in Canada is Gardiner Express Parkway with an average age of 32 years with 1.8 billion to fix them all. Concrete, they're not lasting. So in my lifetime, when I started as an undergraduate in the early 70s, till today, we've witnessed this great move out of timber in our major road networks and move in concrete, and they're not lasting, and their maintenance costs are going through the roof, and owners are looking back to timber. That's why timber is coming back in, because of its characteristics. And these webinars are about how do I build and maintain and inspect and restore timber bridges in the right way to extend life, not shorten life. And when we practice positive techniques to do that, they will last. And timber bridges can outlast concrete bridges easily and be lower in cost of maintenance. So governments struggling with this 269,000 timber bridges of a total of 910,000, all of them in rural areas where volumes of traffic are low, and they can't justify spending the money to take out an old timber bridge that's carried on the asset registry at $50,000 and put a new one in that's concrete for a cost of $6 million for 200 or 300 people that drive it across it a day with 20 heavy load trucks that might get on it. So what do they do in that situation? They press politicians to give them money to replace bridges based on a priority scheme that's come about because of their inspection techniques, where we prioritize bridges, timber bridges, for replacement, instead of looking at them from the point of view of a valuable asset and saying, what can we do to extend their life? You see, that's the key here. What do we do to extend the life of a timber bridge? Instead of saying, what can we do to prioritize them and take them out as soon as we can and put a new concrete one in? If you've gone through an undergraduate program as your training for an engineer, and you have never taken one single course in timber engineering or one single course in timber bridge design, maintenance, restoration, then you get in your position, raise up in your senior engineering level, and get to looking after a bunch of timber bridges. What are you going to do? You stick with what you know, steel and concrete. It's nobody's fault. It's just the way it is. And what we need today is education. That's why I put on these webinars with CWC and MLB and others, because I'm passionate about doing the right thing with timber bridges. We want to save and extend the life of our timber bridges. We want to build new timber bridges. We want to bring timber back to where it was at the 1900s and use advanced concepts and techniques to inspect them, to restore them and build new ones, and bring timber back into play as one of the 3 major materials used to build bridges, and caused a bunch of great things to happen when we do it. If we take an average age of timber bridges in the world today at 82 years, with many over 100 years, how is it that today many engineers say that the bridge reached its end of use by date by 40 years? Who said that timber bridges last 40 years? We need to find a reference for that. The fact of the matter is there is no reference for it. Timber bridges don't have a use by date. And many of the timber bridges we have in the marketplace today are already double that age. Well, why do we say get rid of the timber bridges? Well, one of the key reasons is we don't know how to maintain them. And what we do to them shortens life. And when we do something to them that shortens life, it increases maintenance costs. It reduces ratings, and it brings the risk of failures up. And engineers are risk adverse. These are stats now. Decks last an average of 15 years, superstructure girders 25 years, and sub 35 years. With this longevity, no wonder bridge owners want to get rid of timber. No wonder they say the maintenance costs are too high for timber bridges. You see, I'm about changing this because these features, these facts don't need to exist. Why not make decks last 45 years? Why not make the superstructure last 75 to 100? Why not have substructure piles that last 200 or 300 years? It's possible. We do it. We can do it. We are doing it. And that's what I'm here today to talk about. We can use advanced technologies like high-strength fiber reinforced polymers, where we use these in strategic positions to enhance capacity, to compensate for reduced capacity that has occurred because of decay, for example. We can take these long pieces of fiber that come on a roll that are 5 times the strength of steel at a fifth the dead weight longitudinally in strength, and no strength perp to axis, so that they can be put on a piece of wood and go with the wood and shrink and expand without causing delamination, and enhance the capacity of things in situ. This is a teaser slide for next week's webinar, where we're wood welding things, where we take shear plate pilot holes, and instead of leaving them in open holes where they can use this guy right here, put them in this hole and have slip distortion. You know, it's a point of interest here. In Canada, we have no slip distortion formula calculations. We don't consider slip distortion. It's not in the code. Yet in America, we do have slip distortion, where we consider the impact of these shear plates slipping against the shoulder of the route and leading to slip distortion, and a creation of a modulus for same is part of how we would design. Well, if we want a wood weld, what about the concept of infilling this pilot hole with a 2-part epoxy and freezing the whole thing up and using RP, reinforced polymer, to join things together? Infill this pilot hole, glue RP to the face, separate it from the steel with a saran wrap so that it doesn't glue, because the steel has a 3-fold difference in coefficient of thermal expansion. Use the continuous piece of RP that's on the bottom of this to double the capacity of the glue lamp, create a wood weld, and extend these beam lengths from the shippable 17 meters to 35 meters like you see here in the background, and assemble it with a proper camber and lift it into place behind you in this gap, and do it economically and carry truckloads and have a girder that weighs 1/8 the same load capacity girder in precast concrete, so much so that precast concrete in this gap is $6.5 million, and the cost of a reinforced glulam girder bridge with driven timber piles is under $2 million. We do 3 bridges for the price of 1, and post treat everything after machining so that it lasts 100 years. This is what we're talking about. This is the new timber bridge. These are the concepts and ideas that nest themselves in the idea that timber bridges can last, they can carry heavy loads, and their maintenance costs are lower. That's what we're here to say. So that's a teaser for next week. So timber can be quite durable, but durability depends on quality of the wood, the preservative, the use of the environment, loadings that are applied. Timber does not behave in a truly elastic mode, but has kind of a time-dependent behavior. It's kind of different, isn't it? It's not the same material. One of the hardest things I have to do as a senior engineer at WRD is to hire older steel designers. It's a very difficult job. And my favorite is to take younger engineers that have, a lot less experience and help them understand about timber and train them about timber and have them become timber engineers. Why? Because they don't have to retrain bad habits. Wood is anisotropic, steel is isotropic. Wood is hygroscopic, it breathes in and out moisture, and when it does, it shrinks and swells. Steel doesn't. Wood doesn't expand nearly as much under temperature change as steel. And when wood shrinks and expands, if you've frozen it to something where it can't shrink and expand, what do? Introduce tension perp to grain forces, and tension perp to grain is wood's weakest strength direction in an order of 0.1 MPa. So understanding how to design with steel is pretty critical. So let's just set up the foundation for ourselves, the basis by which we design wood in an advanced way. After all, it's the fundamentals of wood that really create an understanding of building blocks that you use to grow your design capabilities as an engineer. It's important to cycle back and think about, what is this material called wood? And what interesting characteristics does it have that are positive for us when we're designing a bridge? We're driving piles. You can see in this, in the old days, why did we use timber? Well, when we reached a gap, we were building the railway west, and the Iron Horse was waiting behind us to get across that river. We had to figure out ways to do things rather quickly. And so wood was readily available. We cut the trees down behind us in this right-hand picture. We skinned off the limbs. We used the best of the ones for driving piles. And if we had a granular soil with not a lot of capacity, we would drive a high paper pile from the tip of the tree. And so that's how we created pile bents. As you can see here, 2 plums and 2 batters. And we got a train across. And location, like real estate, was everything. And around the world, what did we use? Well, in the northwest part of the United States and Western Canada, we used Douglas fir. It was there. In the southeast, southern yellow pine. In Australia, we used mixed Australian hardwoods. All around the world, we used the materials that were readily available. And these materials were available in great supply at low cost, and so were the cost of manpower. And we built these great bridges and logged out logs. And these logs, like out here in the West Coast, these are big logs. You had to join 2 buck saws together, weld them at the ends in order to be able to cut it down. That was quite a job to cut that tree down. Look at this one, starting out with an axe to do this. These are big trees. And these sorts of trees provided the wood basket for building structures and infrastructure all over the world, dimension timber and round log alike. And this material became the predominant material for infrastructure growth 100 years ago. Cutting big trees down, cutting them up, 1 tree, 1 train, and sawing them into lumber and building infrastructure. Well, today we often look back and we say the big wood's gone. We say good wood is harder and harder to find, and the big trees in Vancouver Island, for example, they're in parks. And the environmentalists don't want us to cut down the old growth because they want to have a few old big trees for the kids to see. And they want to have an opportunity to see and kind of relish the size with which some of these trees can reach. Like the General Sherman tree, where you can drive a car through it in California, or the President, a huge tree nearly 50 stories high in California. These interesting large old trees have been preserved. Well, we say because of it that good wood is hard to find, thinking that somehow this old growth material is all we can really build a new timber bridge with or fix an old one with. Well, that's just not right. So in the Petrified Forest National Park in Arizona, I was going across the country with my son one time, and I took him to visit this Petrified Wood National Park. And here we find Douglas fir logs exposed from the ash that were 250 million years old, that were in the great inland ocean, that when the water receded, they dropped to the floor. The Cascade West Coast Range ash that come out of volcanoes covered them. And the trees were under high pressure and mineralized and basically became agates. And as you can see here, these tree trunks are still there today. It's really interesting. And what they've done is look under a microscope and identify that these trees grew the same way 250 million years ago that they grow today. The bark was created at the cambium, one side of the cambium, it protected the tree. The inside produced an early wood, late wood, which formed annual rings, kind of representing kind of 1 year of growth. This wood in its growth and its heartwood and sapwood has kind of been doing the same type of growing for nearly 250 years. So the concept that good wood is hard to find because we can't cut old growth just isn't true. Regenerated wood serves many great purposes. Trees that are under 100 years old, particularly softwood trees, convert way more CO2 to O2 than old growth trees. So regenerated forests that have been replanted and growing new are good for the environment and are renewable. They're a renewable resource, and we can take the wood we can get from them and build new bridges and restore old bridges, just like we've always been able to do. The key is understanding wood, understanding what it means to say boxed in heart, where I take this wood and I saw around and take the jacket wood, that's the outside wood, which has the least number of knots and has the most clears, and make my 2x6s and 8s out of those for Home Depot and Lowe's to sell with a SKU number. And then as I turn and saw around and get to the middle, I saw a big square timber that I can use for bridge manufacture. And I keep the pith in the middle so that I have a boxed in heart. Why? So that when it shrinks evenly, because the shrinkage tangentially is double the shrinkage radially. And if I got a boxed in heart, it kind of shrinks kind of square. And so knowing that about timber is pretty good. Well, the treaters, they like Kent wood. That's wood that's sawn out here with no boxed in heart. Why? Because it's got more sapwood and it's easier to treat and get uptake and depth of penetration. So as engineers, we kind of need to know the difference between what? Kent wood and heartwood, boxed in heartwood. And we need to kind of know the difference for treatment. And where do we want to have the best treatment and where can we sacrifice a little less treatment? So you can see here, for example, Doug fir. It's a Doug fir log. The first 20 years are juvenile wood. They form the heartwood. That's the inert portion of the tree. This is the sapwood here. You can see much tighter ring structure. Well, that isn't happening by accident. How come this is happening? Because the cells grow around the tree. And I'm going to just stop here and I'll go over to the board for a minute. And I think you can see, well, here's a round log right here. How do cells grow on this tree? Trees grow volumetrically. If I have a tree like this, and this is my trunk, it's growing volumetrically. It grows radially. It's not grass. Palm trees are not trees, they're grass. They shouldn't be called trees. Trees like maple and Doug fir and southern yellow pine, they're trees that grow radially. And what does that mean? I have at my home here, not far from here in Lower Cape, New Brunswick, we have a maple tree out front that's 250 years old. And there's a branch on that tree, and there's a swing on that tree. And my dad's dad swung on that swing because the tree has been on the household property for 5 or 6 generations. And everybody has been able to swing on the same swing for almost 180 years. Well, if tree was a grass, that wouldn't be the truth. Be growing from the tip only, be going up all the time. But trees grow volumetrically, and that swings in the same spot it was 180 years ago. So how did it grow? Well, the tree added cells all the way around, like this. And so when the tree's smaller, it has more early wood and smaller, less late wood, and the cells have to add a shorter circumference. And once it gets bigger, they add a longer circumference. And so the cell annual rings get a little thinner, tighter. It's slower grown because of this distance. Well, why does it shrink and expand differently tangentially versus radially? It's because in this direction, we have cells that are all in a line. They're all early wood. In this direction, we have cells that work from heartwood to sapwood. And in Douglas fir, for example, the shrinkage from fiber saturation point, which is around 26%, to oven dry is like 3.5% radially and 7.5% tangentially. And so if I cut a boxed in heart, it's going to shrink more evenly on all sides. If I cut a cantwood, it shrinks more on this face than this face. And it will look like this after it's dried. And so if I've got that piece of wood sitting on a cap, it creates instability by shrinkage. If I've got a boxed in heart for a cap, it's better because of less instability because of bearing. And so that's how trees are growing as they grow volumetrically, that impacts how we use them as timber engineers. So this is a round Doug fir tree here. Obviously, it's in the round, and we were testing it. You can see the juvenile wood, usually 1 to 20 years. You can see the later wood here, tighter grain. The cells all add around this, and they grow longitudinally. This is the trunk of a Doug fir tree with big bark. As you look up the tree, you'll see something very interesting. It's growing straight. Why is that? Because softwood trees are geotropic. They grow in response to gravity. And their specific gravities are generally lower than the specific gravities of hardwood, which is a phototropic wood. Hardwoods grow phototropically. They respond to light. They reach for light. And when they do, that causes slope of grain and sawn timber out of them because they're bending, they're crooked, they're twisted. Softwood trees grow straight up and down. And that's because they're geotropic. And Doug fir has 2/5 the height in its crown, which means this big clear length here would have no branches. What does a branch do? It forms a knot when you saw the timber out of it. And the knot is denser than the rest of the wood, but it creates slope of grain. And so that's why the wood is weaker, because of slope of grain. We'll get into that in just a moment. So this phototropic nature of hardwood causes it to grow in response to light. Geotropic response of softwood grows in response to gravity. It's got slope of grain that's driven by the axes that the piece forms against the growth. Stop share over here. So now I've got this piece of wood, and it's sawn from a round log like this. And here comes this log like this, tapered. And I saw a piece off of it. This angle that the sawn piece forms with the trunk forms a slope of grain, so that when I look at the side of a piece of wood, here's the grain. And that angle right there is slope of grain. Why is that a problem? Well, because wood is anisotropic. Wood is anisotropic, meaning different properties in different directions. Well, okay, so you get different properties in different directions. What is it about this slope of grain that takes the anisotropic nature of wood and creates trouble for us as engineers? What is it? Well, when I saw a straight piece of wood out of a tapered bolt, I end up with the axes of this wood at an angle to the grain. If I put this in bending, the bending forces can be resolved to tension parallel to grain and tension perp to grain, and wood's tension perp to grain value is low in terms of its strength. And the more the slope of grain, the more resolution of stresses to perp to grain and tension, and the weaker the wood is in bending, it's the tension perp that gets you. And so we want low slope of grain. That's what forms up structural select wood in our grading. Now, when I have a knot, what happens to the grain? The grain follows the knot around. And so if I get a knot in the bottom face of my piece, it causes a slope of grain, a big one. And that resolution of stresses causes a bunch of tension perp And the knot is the defect, the localized defect, the naturally occurring defect that leads to slope of grain, that leads to reduction in capacity. It's why we grade things for knot size. Then we keep the big knots out of the bottom face and tension. If you're designing heavy dimension timber beams, there is an upside down. When I went to school at the University of New Brunswick, nobody taught me in my forest engineering degree that large dimension timber has an upside down. Why didn't they teach me that? Why did I have to install a bunch of girders and have half of them fail ahead of the other ones before I finally figured it out? The reality of it is, when we're not teaching engineers about these issues and teaching them about steel and concrete, what will they use when they get out in the marketplace? Steel and concrete. And when they install the new girders in the old bridge upside down and they prematurely fail, the owner of the bridge says, to hell with timber, put a new steel and concrete one in. I can't pay the maintenance cost anymore. You see, that's not wood's fault. That's not wood's fault. And understanding that is important for us if we're going to properly design with timber. At the tip of a tree, there's a hormone called auxin that tells a tree how tall to grow, where the roots go, the whole deal. And the root growth kind of looks like a microcosm of the crown of the tree up top, only underground. And the tree, as it grows, forms a microfibril angle. On the northern hemisphere, trees grow and twist from left to right. In the southern hemisphere, they twist from right to left, just like the water in the toilet bowl if you're in Australia. And so trees have a radial direction, a tangential plane, and a longitudinal plane, and they're different. They have different characteristics. Wood has 9 degrees of freedom, 3 Poisson ratio, 3 rigidity modulus, and 3 modulus of elasticity. That's a big deal if you're using structural software that only allows you to have 1, 2, or 3, and you're putting loads in a structural software for an assembly of wood, and the wood hasn't been modeled with 9 degrees of freedom. Guess what? The results may not represent your true stresses. So timber's properties are based on orientation of the grain and the direction of the fiber. Its density bears directly on its properties. Typically, the denser the wood, the higher the MOE. The denser the wood, the bigger the increase in capacity per to grain. But not all characteristics go well with increased density, because hardwoods could have an increased density, but much greater slope of grain, and the slope of grain would make it very, very weak. And if I couldn't drive a nail in it and I had to drill everything with holes to put bolts in it, it wouldn't be user-friendly. Thus, Douglas fir and southern yellow pine became the wood of choice around the world. Their specific gravity was 0.48 to 0.54, the two of them. That's about half the density of water. That's why specific gravity is about 0.5. They could still be nailed without splitting and checking, breaking the nail. They're relatively strong. If you sawed them in the right bolt, you could get low slope of grain. And then if you graded them for knot splits and checks, conditioned them and controlled their moisture, you could improve their dimension design properties. And so these types of woods became very popular in the world. In Australia, Doug fir became known as Oregon pine. And so we see them used all over the place. And timber properties, bending, stress and tension, compression, parallel ground, all these different properties were reflected in the wood made up of a cellular structure. Cellulose, hemicellulose, glued together with lignin. And that's what formed up wood. And you notice that this piece here, how did it fail? It was in the roof system of a pulp and paper plant in Washington State. And it had reaction wood. And it was called compression wood in softwood beyond this webinar, but reaction wood in softwood is compression wood. Reaction wood in hardwood is tension wood. And it was put in the wrong place in bending and led to failure. So we need to understand these characteristics of wood. So timber properties are based a lot on how it grows. It has localized defects like, knot, slope of grain. These things all get considered when we're developing design values. For example, with wood, the composite adjustment factor that is used to calculate the design value for strength properties is based on 1.3 for safety, like concrete and steel, the same kind of safety factor, and 1.6 for duration of load, because wood tends to creep. It's got a viscoelastic lignin, that's the glue, and it will creep under constant load. So we change this 1.6 effectively by using a CD factor in Canada, or load duration factor. And our current design values are based on the assumption that our live load will have a cumulative life of 10 years on our timbers. If that cumulative life of 10 years is assumed to be longer because of higher percentage dead, we factor down the strength, effectively increasing the 1.6 DOL. If the load is going to be less, like wind or impact loads, we factor it up by using a different CD value, 1.25 or 1.15 for snow, for example. And so we change the properties of our design to reflect this organic material called wood that's growing with rays and longitudinal cells and structure that are the way nature grew it. And this microfibril angle, as we talked about in the northern hemisphere, going left to right, is smaller in Doug fir. It's why it makes excellent piles, or the same with southern yellow pine. It's larger in hemlock. I wouldn't really try to drive a hemlock pile because it would tend to shard. Its microfibril angle would get you, and it wouldn't put nearly far in the ground with the 20,000 foot-pounds of dynamic energy, so that you use to drive them, for example, with a drop hammer. So this is a growth pattern here. You can see a pile. He's turned upside down because the difference between a pile and a utility pole is a utility pole was in the ground butt first. A pile was in the ground tip first. And you can see the microfibril angle here, and it kind of brought the checks to bear as it dried out. This guy's in the southern hemisphere. This guy's in the northern hemisphere. So the difference between shrinkage in wood and steel is obvious. Steel doesn't shrink when it gets water on it, doesn't suck up water. Wood's a naturally occurring organism. It sucks up water. It's like a sponge on your sink side. It dries out and shrinks up. When you put it under the tap with water, it sucks up water and swells up. That's what wood does. And it starts to do that when it hits its fiber saturation point. That's the point where the water in the cell wall has saturated the cell wall. That's fiber saturation point. When wood picks up more water and it goes into the lumen, it doesn't shrink and expand anymore. When it loses water under fiber saturation point, it does shrink. And the cells within wood go radially, vertically, and they're all the same. They're hygroscopic and they're anisotropic. They have different properties in different directions because they're longitudinal in nature, most of them, whether they're rays going across the ray of the radius of the wood, or cells going up and down the wood. They're longitudinal in nature. That's why they make great paper. So fiber saturation point has got bound water and free water. When I get a spruce tree in the Maritimes and I cut it down, in the winter we used to cut our wood because the moisture was kind of out of the tree a bit, and we could put it in the spring breakup and float it down the river. Well, when I cut it down, I might have 70, 80% moisture by weight, or 90. Sometimes wood can have 180% by weight. It weighs a lot more when it's sucking up the water than it does dry. And so this wood in the what we call free water, or lumen water, L-U-M-E-N, the lumen water doesn't change the dimension of wood, but it certainly changes the weight of wood. And as it dries out down to 28%, the bound water begins to leave, and then it shrinks. And generally speaking, when water dries out of wood, it gets stronger, generally speaking. So the drier the wood under FSP, the stronger it gets. So if I put a strain gauge, let's boil this down to something practical. If I put a strain gauge on the bottom of a piece of Douglas fir that's on the bottom of a truss in a through truss bridge, that strain gauge isn't going to act like a strain gauge put on this piece of steel. What happens with it? When I put a sender on it, connect it to a gateway, and record strain from truck traffic remotely, I have to be considering more than just the truck traffic. Look here, here's the tide going up and down underneath the bridge. Watch what happens to the strain as the tide goes up. That's a steel foil gauge placed longitudinally parallel to the grain in the bottom tension cord right here. When it has a tide come up underneath it, slowly that timber picks up moisture, and when it does, what's it do? It wants to expand. The steel foil gauge doesn't, and it registers as what? Tension. So you see this increase here, just following slightly behind the tide. We need to understand that to put control gauges in place to be able to synthesize out the real strain by taking the effects of RH and moisture content change out of the equation. Understanding wood is important for the real purposes of, for example, monitoring bridges. So you can see, as I said earlier, there's the tangential direction, the radial direction, and the longitudinal direction. And wood basically is shrinking negligible amounts, 0.1, even 0.01% longitudinally. That's how we can take and use stud wood in the Maritimes to build houses and not have them settle. Well, in the Maritimes, if you buy a log home, you know about putting spaces above your windows and doors, because when the log home dries out, it'll seize up all your windows and doors if you haven't left spaces. Why? Because it shrinks that direction a bunch. And if you build a 6-story hotel and you have your stairwells and headers at the top of your each layer of the building in a platform framing, what happens? That timber, the 2x12s, can shrink, and you can find your stairwell in problems if it's steel. You have to have slips. And that's the nature of wood, is it shrinks a lot radially and tangentially, but very little longitudinally. And that's why these shrinkage checks in the end of logs look oval, because the tangential shrinkage is double radial. And that's why they look this shape. That's a naturally occurring check. Why? Because end grain travel of moisture is 100 times faster than side. That's why things end split. It's why they try to put nail plates on the end of pieces of timber to try to keep them from splitting, because it's 100 times faster end grain travel than side. So what do we do to kind of control this? The old ways of putting stress kerfs in. It allows air to get into the center. It's a non-structural change to the wood, and it lets it shrink and dry more evenly in these boxed-in hearts. And in the Boise's farmers market in Fredericton some 35 years ago, I was practicing this technique as a young engineer designing timber, post and beam frames in the Maritimes. So these vertical cells have microfibril angles. They run parallel to grain. The microfibril angle can create a slope of grain, as can the axes of the wood cut against the grain of the wood itself. So these characteristics of wood are driven by hygroscopicity, anisotropic nature of wood, and its characteristics such as density and knots. And we can core out a piece of wood, take the core and check it out and do an ASTM standard test and determine its specific gravity and its moisture content, outer, inner, inner, outer, through the piece. And we understand the moisture contents of wood and timber bridges well, because now we've got close to 2,000 samples over decades of wood tested from different bridges all over the world. That's how we know moisture contents. We can use these small cores to identify them as coastal Doug fir, for example, and understand that coastal Doug fir doesn't have what? It doesn't have blocked up pits that can basically mean they're aspirated and won't take side grain travel of moisture and of treatment, more importantly. So we usually like to treat coastal Doug fir timbers for use with bridges, because its species, whether they're softwood or hardwood, kind of grow in a way to form up branches, heartwood, sapwood, and density, and all these knots can impact the properties of timber. So as you see this fissure, for example, that's not a shear crack, that's a shrinkage crack. It follows a ray. A ray is a cell that went radially, and it was kind of in between the cells that go tangentially. And so when the cells tangentially were shrinking a bunch, 7.5% from FSP to 0, the stress relief came along a ray line, and it was a fissure formed or a check. And when engineers go out and see timber in the field, they often confuse checks with shear checks. They're not the same. We need to know what the difference is, and we're going to get into that now. Timber maintains its strength with increasing temperature all the way up to 150 to 175 F. It's pretty good with the temperature. It doesn't expand like steel. It doesn't blow the joints out in the building under even low heat fires like steel will. Its moisture sucks up moisture. It reduces the modulus of elasticity as it increases in its moisture content beyond fiber saturation point. Particularly, wood does not change in characteristics. Below fiber saturation point, it does. So design properties can really drive the equation with wood. You can see this knot. He's on the upside, which is good, but look at that slope of grain. When I put him on a test jig, he fails in tension perp. That triggers an MOR, a modulus of rupture and bending. Grading agencies are set up to help us define wood. And what's their purpose? Well, if an engineer sits in an office and designs a bridge, assuming number 2 or number 1, he puts it on his drawing, then it goes out to tender, contractor picks up the drawing, wins the bid. He has to be able to go out and buy something the engineer designed. So there are grading agencies that are in place to help grade lumber consistently so that engineers can use a grade, contractors can understand that grade and buy that grade. And so these different agencies are set up around North America and the world to help sawmills and providers, manufacturers, grade their wood in a way that engineers understand. When they grade their wood in large dimension timber, they allow bigger knots in the compression zone of large dimension timber. If engineers don't understand this and the contractors don't understand this, there's a 50-50 chance that even a number 2 or number 1 or a structural select timber is going to get in upside down. When that happens, big knots get on the bottom. When that happens, slope of grain triggers premature failure. And so we don't like that to occur. So I'm hoping that everybody that's online today can understand these important factors in their own design world. Design properties in tension and compression parallel to grain also trigger mechanisms of failure in wood. You can see here this localized, what we call plastic shift, or by the yield point in compression. And this is what goes on with this column. As you can see, you're sliding by one another. Piles will find localized zones of MOE in compression that's weaker, and they'll find plastic shift. And the plastic shift will occur in different points of the pile under excessive axial load, where that yield point and MOE in compression is lower, and that's where you have these failures. These failures are not nearly as bad as tension failures, because tension failures often lead to immediate global collapse, whereas localized compression failures don't. So these are differences between tension and compression testing. We can do compression perp. Another interesting thing for engineers, compression perpendicular to grain strength values are not strength values. They're specific values. They're the load, the stress that causes an 1/8 of an inch deformation in the piece at the reaction. It's confined to the bottom half or third of the beam. And the reason in Canada we have what we call opposite side compression factors for bearing that are more aggressive is that if we have bearing at top and bottom at the same location in a piece, a horizontal piece, that creates double the deformation, thus the reduction factors for it. It's a specific criteria. There's no composite adjustment factor used in that value. Because it's a specific criteria, it shouldn't have dynamic or any other strength reducing factors applied, other than moisture content and some similar ones. You can see in this design property here in bending, you see this round log. People ask in Canada why round log values are so low. Well, it's because we just haven't used them much, and the values for round logs and bending are kind of based on empirical smoke-filled room properties. In Australia, you can take a round log, for example, and have an F27 or a 27 MPa allowable stress design value. The minute you saw a piece of timber from it so that slope of grain comes to play, its value drops from 27 MPa to 17, 22, maybe, or even 14 because of slope of grain created by the axes of the saw. You can see this guy here. Ooh, does that look like shear parallel to grain? It's at the end of a piece. Well, look at this little piece of wood here and get your tip. Typically, when you see pieces of wood attached, they're not horizontal shear. When I grew up, I wished I'd have had somebody teaching me that horizontal shear, the value for shear was not transverse. In timber, what governs is longitudinal horizontal shear. And you can see these shear values for those in the group that are interested. The late wood, early wood interface is where 66% of all horizontal shears occurs. That's where the wood starts to grow again in the spring. The lumen's the biggest, the wall's the thinnest, and horizontal shear is the lowest. And you can see it here in this piece of these pictures. So the codes and standards in Canada, what are they for? Well, National Building Code for building with timber, CSA 086, for example, or NDS in America, are for designing with timber for engineers. What do the bridge codes do? The bridge codes like S6 in Canada or AASHTO in America or 5100 in Australia, they stand between the timber design code and the site for a bridge designer. S6 Part 9, I'm on that committee, is an interpretation of how 06 applies to a site with specific reference to highway traffic. That's what it's for. And 08 is 080, for example, here, CSA, is about how we preserve them. So these standards are to help engineers design and utilize timber in the correct way. We rate timber bridges, we rate existing bridges with section 14 of S6, for example, which in itself reflects back on part 9 and 086 in terms of helping engineers understand rating of existing bridge. For example, if I'm rating an existing bridge that's seasoned, I wouldn't have to consider it green. If I'm building a new large dimension timber bridge, I have to consider most of its elements green because they go into place green. If I'm in a tactile inspection, I can consider them dry because the average moisture content is 14 to 16 under either closed or open deck bridge. And what I couldn't consider as dry would be the connectors if there were vertical fasteners that originated from the top. I'd have to consider those green because I let the water into the bridge in its core through the fastener. So codes and standards in the United States work the same way. International Building Code, we have the National Design Standard. AASHTO stands between it and the site, and we have its AWPA, the Wood Preservation Standard. So how do we get what type and quality of timber that we want? Well, the industry has set up these grades. The engineers have designed according to the design standards, specified the grades, and contractors are buying them. And these grade agencies, like I said, have identified these knots. Just kind of a little review here because it's important. Conditions for decay. You know, in an in situ bridge, decay accounts for 82% of all timber bridge degradation today in the world. It's not impact load. It's not salt on the road. Contrary to all those opinions, it's due to fungal decay. And the conditions to create fungal decay are pretty specific. You remove any one of them, wood bridges don't decay. Oxygen over 21, moisture over 22, temperature in a 5 to 35 range, and of course, wood is the food source. And to know just how specific it can be, you know, this is the HMS Investigator, locked in the ice, trying to find a passage to China over 100 years ago. The guy's going across northern Manitoba, comes across the piece of wood sticking out of the snow. He marks it, goes back, digs around it, x-rays, and voila, they find the HMS Investigator locked in the ice, and it's been there the whole time, skeletons underneath blankets, the whole thing. The wood is as perfect as the day it was put in the ice. Why? Because the temperature was not in a zone where the flow of fluids through the hyphae, this is a spore causing hyphae, would not take place, and the wood was preserved. So because wood is hygroscopic, it can suck up water and lead to more decay. Well, this guy's fishing up a southern yellow pine log, not because he's interested in getting in with the gators in Louisiana, but because he wants to get at that wood that sells for a big ton of money for southern yellow pine flooring. Now, why is the wood worth hauling up? Well, because it's been submerged and there's no oxygen. It hasn't had the 21% oxygen. It's been waterlogged. And that's why I laugh at engineers that look at timber piles going under the ground. And if they spec a new foundation, what do? the old timber piles out at great cost and then drive new micro piles for mud sill piles. And I'm saying to them, listen, those timber piles that are in the ground are as good as the day they were driven. There's nothing better to use as a mud sill pile. Because why? Because the oxygen has not been there for the wood to decay. So if I've got a pile in an abutment bent and I see this depth finder here, you see this depth shield I referred to, XX means it's 20 feet down from here to the tip, and I'm exposing this pile. Why is it that I'd find decay here? Not because there was no oxygen deprivation issue. It's because the silt came in around this over time. And as the silt did, it shut off oxygen and it stopped decaying. But when the time was in the past where it was open to the splash zone, it decayed. And that's why we find decay underneath the ground line in piles, is not because I'm wrong about oxygen, but because it was open to the oxygen at some point in the past. Just like these whales, for example, got buried in or half in and half out, and they're perfect place for decay to occur, as you see here. And we have decay hazard maps in North America, and they follow the rainfall. They follow the content of moisture. And if you look down here where I'm office is in Jacksonville, Florida, look at that. The hazard zone is high. You know, it's 168 to 365 days a year. And I can guarantee you this is true, because if I put a wooden lawn chair out on the deck out back and I leave it, within 2 years, it's done. Because it's decayed. It's just every day. If it's not treated through and through, and if I've exposed bright wood, it decays. So the combination of decay leads to insects, because it breaks the wood's specific gravity down and it feeds on it. And this degradation comes because there's an enzyme secreted by the hyphae that grows in a fungal colony, and that is acidic. It breaks the wood down. When it does, it's edible. And that edible wood is reduced in specific gravity. And as little as a 10% loss in specific gravity can lead to an 80% loss in compression perp, 75 in bending, and 65 in shear. That's why we see compression bulbs at the ends of beams that have got decayed at the ends around vertical drift pin, is because they lose compression perp to grain first and they bulge. Why? Because again, it's a specific criteria, not strength. There's no safety factor. It's the stress that causes an 1/8 of an inch deformation. So I get 80% loss. Why? Because I've got a lot more deformation for the same load, because it's losing specific gravity. So how does fungus grow? Well, it's got a hyphae and it grows cross grain. You can see here, there's white rots growing through the lignin. And it has a foot at the end of it secreting an enzyme. You can see these microscopic shots showing the hyphae here. And this hyphae has got a foot at the end, secretes an enzyme. And people think, well, I'll drive a vertical spike galvanized into my girder down into the cap, and I'll try to get the water to stop going in by using a mastic around it. Doesn't work. Doesn't work, by the way, guys. And I put a vertical from the top in this nice creosote treated piece. And I'm figuring it's going to decay in there, and I'm going to have to replace it in 10 years. So I leave the head exposed so that I can get it out easier. And so I'm accepting the fact that wood screws over at 10 years, even when I buy the premium incised creosote treated piece of Douglas fir timber, and I put a spike in it, vertical drift pin right from the top, put a mastic around it. It still doesn't work. And it leads to decay in this piece in bridges just like this one in Camrose, Alberta. And you can see where it goes. Here's the vertical drift pin. Here's the stress wave time up in the thousands, when 150 to 250 is the criteria. And this is the reds. And this is another shot. Here's up in the 1,000. And here's the reds. And there's what happens when you put the vertical in, the whole thing decays. Beyond the scope of this course, but suffice it to say, look, this is an old cast square head vertical. This is the same connector. It's 150 years old. Which part of the connector is still going? The horizontal part. Which part is gone? The vertical part. Engineers listening, stop designing verticals that expose bright wood and originate from the top unless the holes, the pilot holes, are post-treated. You're doing a disservice to bridges, timber bridges. You're giving timber a bad name, and you're saying to yourself, I don't give a damn. It's a temporary false work anyway. I'll just do it this way. I graduated back in the 70s. My first bridge for Carly Simons and James Taylor off the south coast of Nova Scotia to see the total eclipse of the sun. I got out of school. I hadn't been taught a thing about timber bridges. I opened up the BC Forestry Road Bridge Manual. It was brown, oblong, black binder, soft covered, opened up and poured through and picked off the design details and used them for my first bridge. What a mistake. Bridges didn't last 30, 40 years and they're done. Who wants to have a bridge last 30, 40 years? Just because I put all the wrong details in. It's why today we're working with National Research of Council this coming winter to develop a new textbook called Advanced Timber Bridge Detailing. Something for engineers to look to know how to design their details, to be used at the university level to teach them. Why? Because timber bridges are coming back. They're going to carve out their rightful place amongst the other two materials and be used in bridges across the country. And I live for the day that we drive across the Trans-Canada and see 3 or 4 of them overpass bridges. Timber bridges need to come back to play. Design them right and they'll last a long time and people will use them more. So I'm going to go back to this picture. Here it is. This is the galvanized vertical spike used as a drift pin in a creosoted piece of timber with incising, with a mastic around it. And guess how old that is? It doesn't take a lot of guessing to realize that it's probably in the 5 to 6 to 7 year old range, right? Here's the bottom of it right here. What's this? That's a fruiting body growing out the bottom of it. What's this? That's the hammer hits from the stress wave timer start, where we're hitting it to measure the stress wave time through here. After 5 or 6 years in service, a brand new piece of timber that would cost you an arm and a leg today and an arm and a leg to have the labor to get it in. And they're screwing it over by putting a vertical in from the top when there's 16 ways to do it right. Is a ballast tray deck put on 8-year-old cross bearers, vertical lag screws put in, petroleum jelly put down, didn't work. And they started to what? Mushroom compression bulge. Go to horizontal, switch the verticals out for horizontal, turn the 90 with your connectors, stay horizontal, put diffusers into areas that are subject to some decay because of moisture, and use durable timbers. It's the durability chart here showing the different durabilities, natural durabilities of timber in the heartwood classification of timbers. What are the things that go on when we see wood decay? Change in color, odor, decreased weight, strength, stiffness. It becomes more hygroscopic. You know, decay causing fungi aren't stupid. The first thing they do when they start to decay a piece of wood is make it more hygroscopic. Why? So they can get more water. More water means more decay. What else happens? When you get decayed wood, it becomes more combustible. Its ignition point drops 100 degrees. That's why we can rate bridges now in Canada based on how decayed they are. The more decayed they are around the vertical fasteners, the quicker they burn. Why? Because the vertical fasteners let thermal energy into the middle. It's got a lower ignition point and it burns quicker. And they're more susceptible to insect attack. So what do? We treat them. We don't treat them with waterborne preservatives because what? They leach up against the cell wall and they leach back out the next time it gets wet. Put an oil-borne preservative in there so that they fix against the cell wall. Water and oil doesn't mix. And that's why codes like AREMA don't allow waterborne preservatives in their timbers. They specify oil-borne preservatives. This is a Stanford's Bridge on Victoria, Vancouver Island. It was put together in 3 pieces, the flanges and the web. They had a secondary gluing. The secondary gluing didn't work too well, left gaps in a thick glue line. Water got into that thick glue line down below and formed a decay pocket. And you can see the treatment in here. We knew that they probably weren't coastal Doug fir because the treatment was really shallow. And the laminations were pre-treated before glue. You can tell that by the way they break. And so you can see here what happens. And the engineers found naturally occurring shrinkage checks on the exterior girder specified epoxy. Never works. Don't do it because it always cracks and lets more water in and then acts as a dam to keep the water in there. Let it breathe. Let the wood breathe. Don't use heavy solids, paints and stuff on the coatings of wood over 29%. Let it breathe. So you can see here, cutting the piece. And here's where the piece, this is what caused the failure of the bridge. That's not wood's fault. Nothing fixes stupid. It's not wood's fault. It's designers' faults. It's maintenance faults, utilizer. They should have found this before it ever became a problem, been able to fix it, diffuse it before it gets run away and decay and leads to failure. So in the proper treatment and its effectiveness is a critical thing when we're designing timber bridges. Some wood has this natural durability, others don't. They have to be treated. And we look at inland dug fir versus coastal. It's got tyloses. It is, that's crazy. Just that far, I just went blank. I get all these words and I spin them off and then I run to the end of my tape and I can't keep thinking. It is, anyway, the pits are blocked because they're aspirated. That's the word. They're aspirated. That means the pits have closed up on inland dug fir and they don't let transfer of the treatment laterally in the piece. So you can see here, this is a Douglas fir Kentwood, no pith. It's a Kentwood. We wanted to get it treated. So we incised it. Incising opens up end grain. It doesn't, there's no injections. There's no people with a needle in there sticking a needle in and injecting it. So don't think incising is going on at the treatment type. It's incised first to expose end grain because end grain travel moisture is 100 times faster than side. So they incise it to get more uptake. And this had a pre-treatment of penta, you can see the brown, and a post-treatment of crea. There's no boxed in heart. It's a Kentwood. You can see a spike knot here from a branch. You can see lots of tight grain here, a great piece of timber. Why is it cut up sitting in the river? Because it's just been taken out of a bridge. It was 10 years old. And who screwed it over? The guy who drove a vertical drift pin right into the middle where there's no treatment in here, let water into the middle and it decayed out and left the whole thing done at 8 years. And the bridge owner saying, why the hell am I using timber? I should never use timber again. It cost me a ton of money to send the crew out, take the bridge apart, buy the piece of timber, put it in there. And when engineers that are maintaining the timber bridge see the timber bridge as false work and live for the day that they can replace it with a new concrete and steel one, we have what we have today, which is the blind leading the blind and timber bridges going downhill quickly and owners saying, I don't want them anymore. Let's not do that. Let's change the way we design and think with timber bridges. This is off of Google. Decay prone areas. This is where engineers have been finding decay for 100 years. Why do we still put a drift pin through the cap into the top of a pile? Why do we vertically spike the deck planks to the top of the girders? When this is off of Google, it's not Tingley talking. I just pulled it off the internet. Why do we do it? Because somebody didn't teach timber engineers at the undergraduate level about proper design and connectors. And when they got out, they just kept doing it the way the bridge was designed to start with. And the bridge had been built this way, so they just replaced it in kind. They didn't need an engineer to replace it in kind. They just kept the same design. They sent a crew out and did it the same way they've been doing it for 100 years. How many buggy whips are made today? Not many. Not many people are dying from appendicitis today because we have advanced technologies to save them. Right? We've done away with our old princess phones. We got cell phones now. We got iPhones now. Why is everything in the world advanced except timber bridges? The reason Dave and MLB and others are passionate about this and why we're having the webinar today is to help engineers get into the 21st century with timber bridges. Let's do them differently. How do vertical fasteners degrade timber? No brainer. They let water to the middle. And when you let water to the middle, even after 10 years, it has no shank strength anymore. The first debris field that hits it, this happens. The concrete stays, the timber leaves, the engineer looks at it and says, I should have built the whole bridge in concrete. If I'd have done it, there'd have never been a problem. The ute wouldn't have been stuck on the other side of the bridge. Instead of someone saying, why did I use vertical fasteners that led to decay around the shank of the fastener when I had no lateral capacity anymore and the first debris field took it out? That's what we're saying. Or why did I put sub piles in with vertical drift pins that led to decay so that I had to go to Home Depot and buy a piece of 2x6 to try and prop it up until I could get a new concrete bridge in? Or this guy here, a vertical drift pin here, so that I screwed over the pile royally and led to it being taken out. Or this one here in Hamilton, where I took beautiful beautiful 8x16 Doug fir, and put the deck on with vertical drift or pins, and look at every one done like this. They still did it. So vertical fasteners are ruining them all. Look at this, stick your hands in it. It's vertical fasteners. And just because we put a covered bridge, well, it helps us with some vertical fasteners that are inside out of the wind shadow. But guess what? The ones on the ends, they get impacted too. And excavators fall through the bridge when they get to looking like this. So vertical fasteners lead to this. Whole bridges sailing down the river in Chaleyville because they lose their abutment mooring where vertical was, and the blow-in water at the end of the covered bridge screwed it over. So extending the life of our timber bridges asset is the way forward. They can be built to last a long time. They don't have a use-by date. This bridge in Golden didn't have a use-by date of 40 years, contrary to the engineer of record. We recertified it for another 100. If you do it right, they last. This one at Keystone, they wanted to replace the whole interchange with a new concrete one, $23 million. And they asked us to come in at the last just to inspect it, to confirm what they had thought. We could find 3 bad actors in the whole bridge, 3 bad actors. And they were going to replace the whole bridge. And the only parts that were really bad were these 3 where they put a new concrete slab on top and vertical drift pinned it. And the only really bad elements were the concrete elements. So they had to replace the concrete deck with a new timber deck. And now it's out to tender and will be upgraded in September at a cost of $4.15 million versus $23 million that was in the budget. And we'll put a new timber deck on it for the first time in its bridge life, lighten the load that the bridge has to carry by a significant amount, because the new timber deck is 1/8 the dead weight, and away we go. This is Milky's closer to home, Bayswater Inlet, covered bridge. They ask us to get in and look at it and understand it, inspect it, find the bad actors. So we used rope access people to hang from the bottom, get in there and find the bad actors. Where are they? In underneath the hog jaw assemblies. We drilled a hole to get in underneath and check. Where were the bad actors? It was the steel, man. The embedded corrosion hit worse than the exposed. Every place the old steel was in underneath the wood, that nice salt air coming in off the Bay of Fundy wreaked havoc with stitching bolts, taking them down to 1/8 of an inch in diameter. Look at this. Every place that was bad was the steel and metal. The vast majority of the whole degradation of the bridge was steel and metal. It was not wood. Ferric degradation had led to a few spots. So we put 2 great big beams, 35 meters in there, lifted the whole bridge up in the air so that we could take all the hanger rods out and fix everything, and lifted 100 tons because this was lightweight enough to get across the bridge to get positioned with a 5-ton load limit. And we put FEMs in there to be able to join the pieces together and create this big long beam, and lifted it up from the bottom and put in new reinforced material, high strength fiber, shear panels for the degradation that occurred, built new pre-assembled, post-treated at the ends deck panels, high strength fiber on a roll, prepared full length, 114 feet. And we fixed the shear cracks at the stitching bolts and bending cracks, increased the compressive element by laminating retrocom to it, basically restoring the bridge by attaching stuff to it and replacing certain elements like these bearing blocks, which had been cut post-treatment and of course decayed because of bright wood, and the concrete, which it has its own problems, and fixed it up to pasting new retro bond to restore the concrete from the pitting underneath, got at it and basically restored the whole bridge. One bad area was an area where the steel had lost by embedded corrosion, and we had decay from blow-in water, and it had led to, look at this bearing plate and this hanger rod getting right up in there in the tension cord. You can see it's embedded corrosion loss all over the place, and you can see we got to take it out, and here it is. It's decayed on the inside. This is the lateral strut rod that went through here, and we basically couldn't save the wood at that spot. So we used engineered wood, created a trapezoid with the proper hole for the hanger rod, basically put pieces by it in tension to hold it in tension, pieced one at a time, 1/2, one tension cord at a time, and glued and inserted them in there, fixing this piece by basically inserting in great engineered wood with high strength fiber that ran by it, and glued in place and restored the bridge. Put in shear panels on the outside to compensate for loss of strength due to horizontal cracking because of localized loads that fell between panel points because there are beams resting on top of the tension cord, and put it back in service with advanced engineering ideas like shear panel screwed glued to the piece, tension fiber, and laminated beam packers, restoring the bridge back to its full strength. Not just its full strength, because it was designed for the turn of the century for 12 tons. We now had raised its load rating to 30 tons and restored a lot of bad actors in the process. Healed up the skirting to keep it protected from the rain, got our elements off there, our lift elements, put in some strain gauges all over the place so we could monitor the traffic that was going on it. We've already, after 2 months, realized that the truck traffic is getting at it. 42 tons is the highest we've recorded so far. And we notified DTI in New Brunswick that, hey, we're watching with the cam. We got the cameras on it. We got the strain gauges, and the bridge is getting overloaded so that they can go over and find people and catch them at it to preserve the bridge, extend its life, all the ways, either from health monitoring to high strength fiber restoration to inserts. These are the ways across a broad spectrum we extend the life of this asset. It's 100 years old. We're going to extend its life another 100 years old. It was designed at the turn of the century for 12 ton. Let's raise it to 30 ton, make it more accessible for the community, for fire trucks and other vehicles. Extend life, health monitor, and put this asset back in service and do it at a fraction of the cost of new. And to monitor it, to make sure it's protected, we'll put gauges all over it. So at this point, I want to change. We've got at the wood, we've got at what its characteristics are, we've got at how we extend life, we've got at where the bad actors fall and why they do from decay. Let's talk about now how we get loads and forces into bridges. Impact loads from wheel loads, for example, can get into the steel, concrete, and wood bridges. They do differently. And typically when we look at a bridge, we're looking at weakest link theory. If someone threw the chain off the side of an observation tower in the Grand Canyon and said to you, hey, I'd like you to hang from this chain, and they told you the average strength was 21,000 PSI, and forgot to tell you that the weakest link was good for 25 PSI, who would want to be hanging from the chain? It's weakest link theory that drives timber bridge design. We're looking for that weakest link, whether it's created by slope of grain around a big knot, or whether it's created by excessive checking, or whether it's created by some decay that got in around a vertical fastener. In a deflection criteria, which is a specific criteria, it's a rate of deflection for a given load. We set limits, like in the railways, for example, on a typical 12 to 15 foot span, they set a limit of a 5/8 or 15 millimeters of deflection when a train goes over it. That's its limit. That's a specific criteria. We have the same for bridges in Canada with live load with truck traffic. We say L400 for live load. Now, if I got a 40-meter bridge in the pan, the live load limit is 40 into 40,000 or 100 millimeters of deflection. Well, when a bridge like wood is put in place and it's lightweight for a given load, it becomes very light. And so we don't like to see 100 millimeters of deflection. So we set the deflection limits a little tighter because we can feel 4 inches. Who would like to be on the bridge if it deflected 4 inches? A truck went by it. That would be nice. And so you try to control that through its dynamic analysis. So forces in bridges, we have to look at the force path. How does the load get from the top of the gap to the bottom of the substructure? And the force path usually goes through decks, through superstructure, and through foundations. And it creates a series of stresses. The forces resolve themselves into tension. And these tension stresses are handled in the beam. We get compression in the top half of the beam, the bottom is tension, or in a truss, we separate the tension and compression cords by a lot so it can carry bigger loads a longer span with smaller amounts of material. We use the mechanical leverage of separation, the moment arm. Well, we look at the stress strain curves of materials, we see that steel has a very sharp MOE, very high compared to wood, you see in the red here. So we take advantage of that with wood. I play with that low MOE. I see that as an asset of wood. And the reason I do is because wood will share load better because of it. It's got more ductility. To put it in reference, the failure deflection of a glulam beam is L90, that's length over 90 to L120. The failure deflection of a reinforced glulam is like L20 to L30, L over 20 to L30, lots of ductility. Listen, if you're on a bridge and it's deflected L over 20, you probably deserve to go down with it. Get off of it. You got lots of time. To put it in perspective, what's concrete's failure deflection? Like L over 230, L over 280, much more brittle, much more sudden. You're sleeping in bed and all of a sudden you're in a concrete rubble, as in Florida, because you didn't get the deflection to see it deflecting. It was brittle. Steel is more ductile than concrete in itself because it will go by yield point, as you can see in these curves here, and go into a plastic range. Wood also has a plastic range. So compression with wood, when things resolve to compression, they push things together, and that creates compressive stresses. We can get compression perp to grain, which has a different characteristic because it's specific. It might have a number like 4 MPa. In compression, we might have a number like 10 MPa. And in tension, we might have a number like 18 MPa. And axial tension is different than bending tension for the design codes. So these different numbers are coming from our design guides that we use as engineers. We calculate the applied loads, we calculate the applied stresses, and we see how those applied stresses compare to design allowable stresses or under limit states plastic. So in bending moment, we got a load, wheel load. It creates a reaction where we look at the compression perp as a specific criteria. It creates compression and tension in the form of a applied moment couple, which we resist with a resisting moment couple. If we've got a slope of grain down here because of a big knot, that slope of grain reduces its bending capacity, and it's a reduced resistance couple. And that's what we watch it for. So we test big beams to find out what they're going to do under load. We can calculate a load deflection curve and calculate its MOE of bending. And remember, it has a different MOE for bending, for tension parallel, for tension perp, for compression. These are different MOEs. And a lot of engineers don't recognize that there's a modular ratio within wood. Wood has a different MOE of compression than MOE of tension. And the modular ratio of Doug fir is 1.06, for example. Its compression MOE is less than its compression, than its tension MOE. And these factors are important to know when you're doing PDA, for example. You understand it's axial compression. Don't use bending compression to calculate an axial response. So when we test round logs, another very important feature, here's Beth doing their weightlifting deal. I haven't got the load applied, so don't think I'm in for child abuse. She's in the lab one night when I'm doing some testing. We're testing this big round log to failure. What did we find? Well, the round log moment failures typically occur about a third the way in from the small end. Engineers, if you're using small end diameter for logs, you shouldn't be. Use the diameter at a third point for your moment calcs. So you can see here, we saw it up into timber. We got to look at those knot sizes, as I said earlier, get them in right. Here comes a bunch of beams used to build a big bridge down in Louisiana, long, multiple spans. Creosote treated, they didn't know what the knots looked like. Who knows what upside and downside? They should have an aluminum tag showing you which is up and down. So they lay a bunch of them and they put them all in. They panelized the track. They put a whole bunch of girders in. They see them here scissored, interleaving, and put them all together. Half of them ended up failing within 3 to 5 years, and that does not look good for timber. It's not timber's fault, however. Someone should have told them that there's an upside down. When you pentatreat it or copper naphthenate treat it, you can see the knots, and it's easier to tell contractors and installers and carpenters, hey, make sure you turn the big up. When you don't turn the big up, here's what happens. You get a slope of grain around a big turn down. These guys are in upside down. One goes, then the sister goes, and the first thing you know, you got trouble, and you've caused that by your own lack of understanding of which side was upside down. You can see it here. So you can reinforce them to fix them, which you can with high strength fiber, and get where you're going, fixing these guys. And when you fix them, you can increase capacity a lot. You can flex them, reinforce them, and fix them a lot. So horizontal shear can be a big feature in bridges, particularly railway bridges where you've got high concentrated loads. and you've got multiple loads in a sequence with a train. That leads to lignin fatigue, and that's why horizontal shear is particularly susceptible to fatigue. It's why that fatigue, that strength affected by fatigue leads to a railway factor, where we reduce the horizontal shear capacity with a railway factor. See, this guy right here is another feature of wood that has nothing to do with the strength of wood. It has a lot to do with stupidity. You can see the engineer of record had replaced a lot of these girders because he vertically spiked them. When he replaced the girders, he let them notch the girders with a notch. Differential stiffness, abrupt differential stiffness led to reentrant corner peeling forces or tension perp, which lead to this failure. You can see this freight train's on a slow order, you can hear it. And because it's going slow, you see the cut right here. They thought they'd go further back because this guy failed. So the next one they put in, they cut the notch further back. Guess what? Didn't help. That's not wood's fault, guys. Just for the lack of this. These could have not happened if they'd have done this. These could have not happened if they had done this. This wouldn't have happened had they done this. The simplest things are the best. Slope cutting and notches. We eliminate abrupt differential stiffness and prevent reentrant corner cracking and reduce tension perp stresses, peeling stresses, and tension. Corbels, they're not a landing. They're not a cheater. Engineers, don't consider them a cheater. The corbel doesn't shorten the span. Even if you put two verticals on each side of this corbel, it doesn't shorten the span. It doesn't work. So don't do it. The span is the span. It's a center reaction to center reaction in a simple span. These knot whorls is where the tree will fail because of slope of grain in flexure. So when we test pieces, we look to strengthen the piece with high strength fiber, for example, as a way of transitioning stresses around the knot whorl. Around the knot whorl, we use shear panel to increase the horizontal shear strength at the end of the piece. Shear in wood, a horizontal shear in wood is cumulative and it's length governed. We learned that from realizing that cantilever beams would fail in horizontal shear. Why? Because we didn't have enough cumulative length, and Canada leads the way with shear with their volume calcs. And this year in C9, we're about to increase the base horizontal shear value for Doug fir to 2.0. And why are we doing it for 1.5? Because we're following 0.86. Because so we can use our volume calculations to increase the capacity of wood in shear. Canada leads the way with shear. And see right here. So how do we know this? It's because we test things, use a high definition post trigger, and we look at how pieces fail in bending. You see the chips floating away here. We're understanding how things are failing by looking at them fail. And where did that fail? Well, it triggered where? We thought the LVL piece was enough to shelter off this knot. It wasn't. So when we put him in failure, bang, how did he fail? He failed right there in tension. Tension perp. So these load deflection curves allow us to establish the MOE for each of the different characteristics. We can establish an MOE, tension, compression, shear. We can have a shear modulus, flexure, MOE, torsion, and so on. And forces in bridges come from mass, acceleration, stopping and starting. When trucks come to stop on our bridges, you have to have space at the end of your girders to let them breathe, but you got to have a donut or some spacer in there to keep that stress from pushing it against the back wall, because your rotation bolt at the bottom of the end of the girder is not going to be able to handle that cleavage load. And their same forces apply with acceleration. Thermal forces that can happen because of expansion and contraction due to thermal for your connectors, wind, stream flow from lateral debris fields, earthquakes, vehicle, boat strikes. There's lots of different forces that create stresses on our timber bridges. And these stresses can, a lot of engineers don't understand, well, how do I calculate the lateral load in a railway bridge? That nosing load, because the bridge, the train wants to hunt between tracks, and there's a lateral load. Typically, we'll use in a railway trestle bridge, 15-foot spans, we'll use 25,000 pounds of lateral load on the cap to simulate the nosing load. Or if it's a through truss, we'll use 1/16 of the live to calculate the lateral. And that's how we approximate the lateral due to nosing. We do the same with truck traffic. And that compounds with debris fields if your ARI has the potential for the bridge to come under force from a debris field as the water rises. So these are the types of things that we watch in our bridges in terms of the forces we consider. Independent forces might come from these thermal, stream flow, soil pressures on our abutments. We have soil pressures that we have to watch for that will push out our abutments, like in Saskatchewan, where our piles weren't driven that deep and it's all ash. And when the groundwater table gets up, it puts a lot of lateral, and our lateral forces in our abutments are handled by the girders. Well, if I vertically drift pinned the end of the girder into the cap, into the top of the pile, and it's all decayed, I no longer have shoulder resistance in the drift pin. They're not joined together. The girders can't carry the lateral for the abutment. And what do the abutments do? All want to come in, and they rotate the cap and fall into the river. The other thing that happens with our piles is we get torsional forces. If I've got a steep microfibril angle, torsional forces can be big and hard to handle. And we need to reinforce them with high strength fiber or post them with a standardized posting detail. This is a detail I wasn't taught at university. How did I post something? I never was taught this. Proper rotation splines and off-center drift pins so I can put side plates on it and create rotation resistance, create lateral resistance for a moment, and create shear resistance. And this is not a posting detail. You make a cut and put two big spikes down in here. I don't know who thinks that's a posting detail. It's not. It might hold it there for a while, but if it gets any aggressive action laterally or so on, it's not going to be there. And who thinks this is a good idea? They cut the pile here and put crazy glue on it and wrapped it with duct tape. And then they put the pile cut so that it's horizontal so they can slip the posting piece in easier. Well, you don't do that. That's a batter pile. You have to have it perp to the axes. So that's not proper posting. No, you do a proper posting. You don't toenail them in. And if you go over two piles on a bench, you got to partial mud sill it, as you can see here. Or if you've got a bad pile, you might choose to straddle bent it. I got a bad pile. I couldn't vibrate it out. I had to drive a new one. I couldn't take the cap out because the bridge had fallen down. So I took a few ties out, brought a pile driver in, drove a new pile each side of this bad pile, chain followed the top together, put a transverse subcap underneath it, and compensated for this piece. That's a pretty expensive way to fix a pile, $28,000 on average, when I could have just wrapped the bad actor down here and fixed the pile in situ with a high strength fiber. So this is what torsion refers to in a pile. You can see it here. This is the microfibril angle. It just got into service. It should have better inspected, but it was creosoted and it slipped in. It was a batter pile. The train stop and start. It puts torsional forces on this batter pile. It goes to perp to grain and tension along the microfibril angle, and the rest is history. They have to come in here, put a temporary soldier in here, a batter, to fix this guy. And so wrapping was developed to help heal up piles. We tested them under axial loads, found out that good ductile failure, and we can use wrapping, wet laid wrapping, not a pre-cured wrap that you have to infill with a grout so that it tights. You can't have piles tightly wrapped because when they draw up water by capillary action, they expand, put huge hoop stresses on your wrap, and they tap all your lateral capacity and bending by putting expansion forces on the piece. So you have to allow a little gap in here by using a saran wrap that allows this to slip and allows this to expand. And you then use the fibers the right way. The fibers that wrap around are for axial capacity because they resist bulging in the hoop direction. The fibers that go up and down the pile are for lateral bending. So this wrapping allows us to increase the capacity of a pile. Well, if you don't watch it and you pot your pile, put a polyester zipper wrap, put a cold mixed concrete in here, dry, and infill it, even with a steel cage, capillary action will bring water up in that pile. Expansion stresses can hit 154,000 PSI, and it cracks the concrete and cracks and breaks the steel cage because someone didn't understand that capillary action expands a pile and causes it to put stress on the wrap, so that you end up having to put a new abutment in after the old one was screwed over by the concrete wrap. So moving on from there to pumpers, that's piles that pump. because they're losing capacity or you've got overloading on them, you don't shim a pile that's pumping. Don't shim it. A shim will just drive the pile deeper. This is shimming on steroids. It doesn't work, won't work, and will not work. Don't shim them. If you want to fix them, get down underneath here and expand the pile's capacity by a partial sill, a partial plate, a footing, and that'll save this cap from horizontal cracking because your shear span is doubled due to a pumper. And this isn't the answer either. They took those out of the code using a precast concrete cap to extend the pile of the load without failure and horizontal shear just puts more load on your batters. A rule of thumb, 15 degrees off center reduces your pile capacity 50%. If you want to crack your batters, put a precast concrete cap across them when you got a bunch of pumpers. It'll roll the load out here and your pile won't be able to handle it and it'll flex and fail. And they did. That's in Saskatchewan, right here. The engineer of record says it's amazing how they drove all the piles. They took these curved piles and drove them so that the curve come all at the same point. And I said, what? Well, they used the bad piles in the batters. I said, they didn't use the bad piles in the batters. This precast concrete cap is driving load to the batters because it's carrying more load from these plums over here, and these are flexing. They're breaking on you. So this is one where we're driving piles right now in Dillman's Bridge down by Halifax. These are Doug fir copper naphthanated treated piles. They're what I call COVID piles because they were purchased during COVID days, and they're big. They're tip bearing piles, big piles. And they're driving them here with a diesel hammer, and they're going to finish them off with a drop hammer. And this is part of driving timber piles. It's a great way to do an economical abutment and get where you're going with timber. So this is a boot, a nice boot. Get the right kind of boot, grout it in, the right kind of design here, because you're going to hit till in 8-10 meters maybe. That's why there's so much cribbing in the Maritimes, because there's so much rock outcrop. It's hard to drive piles. So in this case, we had till down 8 to 10 meters. So we could put a nice boot on it, grout it, and then cut off this nut or here, this extended thread so it doesn't catch stuff, and drive it in the ground. You can see the tops here have been cut down so they can drive the first part with a diesel. And that's a diesel coming at it right here. You put the diesel setting, and every time it gets resistance, the diesel explodes in the chamber, goes up, and this hammer delivers 14 to 15,000 foot-pounds, and we drive them in first with a diesel. And then we finish with a drop hammer. And that's how we get that bridge built. And this is putting the PDA, a dynamic pile analyzer, on the pile to check what the resistance capacity is. This is a frost jacket. It's a crazy carpet that you put around in the frost zone that keeps them from getting jacked in the frost time. And this is showing you using that final drop hammer to do the finishing touches. Well, what are typical dynamics of piles today that we use? Typically today, a timber pile can be good for 25 tons, TON. Typically, I drive them to 3 times that. Typically, I look for termination at 1/8 of an inch with 3 blows. Typically, I finish with 20,000 foot-pounds. And in this drop hammer, the specifications I set for the drop hammer, 6 blows at a 4-foot drop with a 20,000 with the over 3,000 pound hammerhead. And the reason I did that is because I needed 6 to get it out of set, because piles set after you drop. If you're driving them and you walk away, they'll set after 24 hours. So I need to break set, and then I'm going to finish drive until I hit 1/8 of an inch in 3 successive blows, and that sets termination. And all these piles terminated. You can see them here finishing off. So how do I test for depth of pile? If I've got the geo so I can rate a foundation, well, I can use pulse echo technology. I send a signal down, back. It's got a transducer pair that basically is measuring time of flight. You can see the hammer start, the stop, and I'm measuring this on piles all over the place. I can check for necking, breaking, bulbing using this device. This is what we used in Nepan, where we had the abutments where there's 25 piles, 5 rows of 5, that held the old steel bridge that weighed 3 times, almost 5 times what the timber new arch span was going to be that's inserted in there at Nepan. Well, we tested them for depth of penetration, and we got the PET values here, and you can see this echo. We take the time of flight in this first series of readings as it tails off, and we get an approximate depth of 23 feet. And you can see here, going in here. And so this is attached on the side. So we can put the sensor and drive them. You can see the sensor. And it gives us a map of what it looks like. We can see section loss and we can see depth of penetration. And this is a table where they give us some ideal speeds. We're going to calibrate now that we have some known depth of embedment at Dillman, we're going to recalibrate the speed so that we can have a better calibration here to use, typically around 12,000 feet per second in a typical dug for a pile. Helps us then rate the depth. That's why you can use that with geo to understand its capacity. So moving on from piles to shear transverse, we talked earlier about shear and longitudinal shear, horizontal shear. This is not the shear that governs in timber. Yes, it's equal to the horizontal shear because of the cube stability, but it's not what governs. It's this shear horizontal that governs. This shear, you can see the failure due to decay. Micro checking leads to a shear problem. This guy here, that's transverse shear failure because he's totally decayed because of vertical fastening at the top. He failed in shear. Transverse shear like this. Can you imagine how much decay had gone on to cause that to fail in 500 millimeters of solid hardwood log? And here's the stress wave timer, 6784, and that's fruiting bodies across this end. That's huge time. No cavity, completely lousy, decayed, frazzy wood. So horizontal shear is what drives it, the shear, and this is the shear we watch for. And this is the shear here. It matures at about 1.9 D away from the reaction. That's where it's parabolic, about neutral axis. 3 halves VA. At the reaction point in a simple span, the shear is 4 halves VA. And the reason we can ignore shear distance D away from the support, because when shear is associated with compression perp, it's increased 50%. And this is where the maximum shear is. But if I'm out here a little bit outside the compression bulb, I can run into shear problems at the bottom. That's why notches are so critical to have them slope cut. So you can see this Mandry was the first one to figure this out in 69. This is the basis by which we ignore shear D away. If you use your volume calcs in Canada, you can't ignore it. You have to consider shear all the way along and resistance all the way along. The percentage of shear failures horizontal at late wood, early wood, I said is 66%. So we did a lot of testing. You can see your shear rosettes used here to establish shear distribution through the depth of the beam across the width of the beam. You know, it's a lot of testing over the years, the last 30 years has gone into this fact to understand where the shear maxes are in a beam and bending. Look at this beam, strain gauge. We established where the maximum shears were, contrary to what we feel like in the marketplace today. When we look at where shears are max, look where the max is. And it works out to 3 as VA, a distance D, 1.9 D away. So these are important data points for engineers to understand when they're analyzing these types of failures. Where did that shear failure occur? At the end, at the bottom, not at the neutral axis. Where's this? Is that a shear failure? Yeah, it's a shear failure. So is that. Look at the duct mud. This is a cord that is stitched with marriage bolts where the marriage bolt was put in the wrong spot. It led to cleavage loads because the simple span was interleaved with the continuous span, led to cleavage results that killed it. These marriage bolts were in the wrong place. This is what I wish I could have seen in my undergraduate days. You know, this is a coal train going down to Seattle, going across the bridge at White Rock. You know, you got interleaved cords with 4 plies. Half of them are simple, half of them are continuous. The shear is drawn to the stiffer continuous element. When he gets into the continuous element, if you designed it as a simple span, guess what? The shear is much higher and it gets shear failed. And what's the white stuff? That's white wood powder that's rubbed up because of this traffic going back and forth, and water from the vertical drift pins above flushes it out onto the side. And where is the shear failure? Well, at the continuous element across the reaction point, shear migrates back up toward the neutral axis, and there's where he failed. And that's a horizontal shear failure. And this is how they fix them. Sister them. Terrible. Because now this just jerks up the track spikes and it's got eccentric resistance, which is not good. So we can calculate that. Here's another one where they fixed it the same way. We can calculate this difference, this shear stress, by looking at deflection or deformation methods, and calculate the difference in shear by looking at stiffness between the continuous and the simple, and approximate it using these methods, as you can see here, to know where to put marriage bolts in packed cords. This is not a shear crack. You can tell because of the bits of wood picked on. It's a boxed in hard shrinkage check, shrinkage check, shrinkage check. You wanted me to test them. I put my credit card in. I say, listen, I'm not going to test it because that's not a shear crack. It's just a shrinkage check. The shrinkage checks are here. So sometimes they are shear cracks and you have to put a shear plywood on them. Like this guy, this is out in Kootenay Landing East, a Pacific Rail Bridge. It's a hard fix for stiffness, strength and bending, and horizontal shear with shear plywood. That allows us to fix these entrance spans where the trains first hit the bridge and create the most damage, coming off a stiffer approach onto a less stiff bridge. And this is at Wausau, where the through plate girder had trains going across it, and we had horizontal shear failure in all the structural cross ties that rest on the lower flange. So we drilled holes, injected under high pressure 2-part epoxy and healed it up. And this is what it looks like when you cut one in half, where we healed it up by injecting. And so kind of leading up to the end of this little webinar here, this is a teaser. This is what we call near end drift bending. It's a tie spacer guard timber in addition to inner guardrail, and you can see what's going on at each one. We're going to talk about pilot hole size. We're going to talk about end distance. We're going to talk about what happens when the inside out of sight isn't out of mind. And that's going to be kind of in our next webinar series, as you can see here. So looking forward to having you all back on the 21st again, as we get into more depth and get into the more of the minutia here about these. And this brings to closure webinar 1, and I'd like to take questions now. Thanks.
Thanks, Dan. That was a great presentation. And just as you mentioned there, we'll open up to questions. So if you have a question, please hit the raise hand button down below, and I'll give you the power to ask Dan the question out loud. Or if you prefer, you can type it in the Q&A section and I can read it for you.
I can't imagine it. They all leave me. They got tired of me halfway through. I'm sorry I'm so fanatical about wood, guys. I got fired, I suspect.
Okay, here we go. Kenny's got a question there for you.
Okay.
Hi, Dan. Thanks for the very comprehensive presentation. And it's quite overwhelming for an hour and a half of a newbie bridge engineer. So I probably do have questions. I just haven't digested everything yet. So
okay, Kenny. Yeah. Well, I make no apologies for my passion about timber. Listen, if I'm not convinced it works, how am I going to convince anybody else, Kenny? I mean, at the end of the day, pardon the expression, but bullshit doesn't baffle brains. The reality is most of what we talked about today is just based on pure science and fact. And the problem is we're ignoring fact. And we're just pushing on, considering timber bridges to be false work, and pushing on to steel and concrete. And I want to turn that tide around. There's not enough money printed in Canada to take all the rural timber bridges and turn them into steel and concrete bridges. If our rural communities are going to still get a fridge delivered from the hardware store or Lowe's or Home Depot, they need to have their bridge plating stay the same. They can't have them all downrated because the engineers come by and get tired of looking at them and can't get the money to fix them and start downplating them. That's no way to serve the community. So what I want to do is change that trend, Ken.
that would be fantastic. And I know in my local community, we have that exact condition. We're getting our local covered bridge replaced with a concrete one. But
exactly.
They want to double lane it, and that's
exactly.
the solution. They don't want to add. They don't want to repair the first one and add another one. They just want to replace the single.
Ken. It's a sad commentary in a forestry nation where many of our design codes lead the way in the world with timber. It's a sad commentary. We have mass timber making such an entrance on the scene now across the country and around the world with high-rise buildings out of timber, carbon-friendly carbon solutions. But yet with bridges, we still ignore the carbon lens. We ignore timber as a equal partner in the material base, and we watch the cost of concrete and steel bridges go through the roof. It's not right. It needs to stop.
I do have a question. Are there locations or bridge types that are not suitable to timber? Like I gather there's a economy of scales for certain bridge types, but you're thinking that the smaller bridges, what would be the typical span? Like you said, 35 meters. Is that a clear
Mhm.
span or is that multi-span?
Yeah, it's clear span. That one where I showed the driving piles, it's 35-meter clear span. Typically we can get through truss spans to 80, 83 meters, easily 100 meters. And my longest is 179 meters clear span. We typically see railway bridges drop to 12 to 15 feet, let's say 4 meters, because they got heavy loads in their old bridges, and that was the design. But with new horizons, with high strength fiber, being able to be continuous on the bottom to cover off localized tension stresses and be 200 feet long continuous. The sky's the limit for you with timber today. With wood welding, we're going to talk about next week in the next edition of the webinar. You're going to see just how easy it is to put together timber and form 35-meter clear span girder under bridges that are an eighth the dead weight of concrete. I mean, when you get to 20 meters, 20 to 22, 23 meters, you're out of concrete sweet spot. When you go across Canada and drive under these overpass bridges, where they have precast concrete girders in place that are 30, 35, 40 meters long, that is so uneconomical, it isn't funny. Like, if I drove the length of New Brunswick and went from Moncton to Edmundston, and I drove underneath all these overpass bridges that you see that are precast concrete, the average saving in a bridge to put them in glulam, FEM'd 35-meter clear span, the average saving is 50%. That brought
I'm just
silence
shocked that we have so many then.
That's it. You and me both. It is shocking. And, it's a sad commentary. I took a bunch of bridges around the Moncton area, and we did a preliminary calculation of the cost of the bridge and the awarded contract. And I don't know how many bridges were in the group. I think it was 5 or 6. And the saving was $100 million. How can we, in a province where we have to cut the budget for our highways and our bridges, at $250 million, and we're in a have-not province, we don't have the money. We have some 56 covered bridges, 1,800 to 1,900 timber bridges in existence, and we're building new bridges that are costing 3 times what they need to cost and ignoring the use of timber bridges. It's just not acceptable practice. And I know I'm not well liked because I say it, but I'm not in a popularity contest. The first guys to talk about new things usually don't get liked. I mean, if the people making decisions have been trained in steel and concrete and they don't want timber, I'm not that well liked. That doesn't mean I stop talking. We live in a free country. What makes engineers strong is transparency. I mean, as engineers, we want transparency. We want to know what the cost benefit analysis is. We want to know the characteristics, and that's what we're here to talk about, Ken, and that's what I want to see.
So are there universities or areas of expertise for rehabilitation of timber structures that are deteriorating? Like I gather that's the
key, isn't it?
That's the conundrum, right?
Yeah, it is the key. Yeah, you just don't have the training. I mean, look across the country and try to find a place where we teach timber bridge design. I mean, I worked hard to get one in Australia and Tasmania. Just opened up a master's in timber design. We got 3 areas, 3 universities that kind of talk about timber engineering. We're getting more into mass timber, but one of my big recommendations to Canadian Wood Council was we need more tools to educate engineers with, and that's why we're going to be developing this new textbook this coming winter with advanced timber bridge design techniques in it. Show engineers, it's going to be 360 pages long, talk about how to do these things. And hopefully we can get universities that embrace it. But here's what happens, Ken. If all the bridges that are designed and spec'd today across Canada that receive federal funding are concrete and steel, there's no marketplace for timber. And universities train our students and engineers to enter the marketplace to be equipped for the market. if nobody's designing and building them, there's no market. And so it's kind of a catch-22 situation that we really work hard against. And, you know, around the world today, you know, there's just not many of us, you know, and so we work hard to convince people. And so, you know, David and I from MLB have a personal strategy to get our first Trans-Canada overpass bridge with timber. If people are driving to Halifax and they're on the Bi-High from Truro down to Halifax and they drive under a few timber overpass bridges, people will say, well, geez, I guess we can build bridges with timber. But yet just off to the side of the Bi-High, you can go over to Dillman's, which as a crow flies is 20 minutes off of the airport and the Bi-High, and see a 35-meter clear span bridge going into place for a total of $1.9 or $2 million. I mean, this is the inevitable. This is where we need to get to. Other questions?
Yep. One from Robert here. Could you please expand on lignin fatigue and shear?
Understand you. So when we've tested, Texas A&M has 2 or 3 key papers. If you're interested in these papers, connect back with me. I can make them available to you. And in these tests, they took girders from railway bridges, and they knew their age, they knew their condition, and they basically tested them in shear to failure. And they found out that when they looked under a microscope, the lignin, which holds the cellulose and hemicellulose cells together, had microchecked. It embrittled because it's a amorphous, it's a viscoelastic. People probably know that in the old days, they made the old 33 1/3 records from wood fiber, lignin. And these records were made from basically wood stuff. Well, this lignin, it kind of fatigues, and when it's got a repeated heavy load, particularly from unit trains, coal trains, the trucks are all repeating the load, and it puts the shear back and forth, and it creates that fatigue in the lignin. And that's one of the things we see under repeated use of heavies. And that's where we see the railway use factor come into play, where they cycle down the shear so that they get longevity. After all, our factors with timber are twofold. One, to create safety for the community, and 2, to extend life. That's why durational load is based on 10 years of continuous life. When we use the CD factor for load, it's about extending life. It's about realizing that if I kind of keep my wood operating in about a half to a third of the yield point curve, I can have it extend and its life go a long time. That's what it's about. Is that answering your question?
Yeah, he was on an older version of Zoom and it wasn't allowing him to talk there. So
Okay.
I did leave my email in the chat there if there's any follow-up questions.
Yeah, we'll send them
I could
publications,
forward on
Dave.
to Dan.
Yeah.
Mark, I'm not sure you had your hand raised there. Do you have a question as well?
Yeah, it shows you got your hand up, Mark. Yeah, okay.
I think I hit that by mistake. Thanks.
Oh, good. So if there's Kenny, did you have another one there, or is that from?
Yeah, I just had a question about what are they called? Kerf shear or kerf slots or?
Yeah, stress curves.
Stress curves.
Mm-hmm.
Do they need? Is that a preemptive pre-treatment measure,
Yes.
or is that something that
Good
you do
point.
in situ?
Yeah, good point, Ken. You know, you use them indoors and outdoors. A lot of times more indoors because they'll reach a lower MC equilibrium moisture content. And so they're a little bit more to keep the wood from twisting and doing funky things, you know. Big dimension timber particularly, it'll twist enough, it'll follow the microfibril angle when it dries, and that'll twist it away from connectors and cause havoc in your connectors. So if you want to keep them straighter, you put the stress curves, and they're non-structural in that they're going parallel with the axes, and they open up interior portions of the wood to allow it to equilibrate better and more quickly and not develop the twisting. If you're going to use it outdoors for timbers for bridges, you want to put it in at the factory or someplace else, you know, ahead of treatment, because you don't want to expose bright. Bright wood is untreated. When I term in this 3-course set, when I say wood, the exposed bright, I'm meaning expose the wood that's untreated.
Okay, so follow-up question to that. Is there a rule of thumb for the kerf stress depth? Is there?
I understand you. There is a rule of thumb. So typically you've got the depth is 3.5 to 3 3/4, a standard depth of a traditional skill saw rotary with a traditional blade. And the spacing is traditionally refined to about a 3 1/4. So on a nominal 8 wide, you'd have 2 stress kerfs.
Thanks.
Yep, no problem.
Okay, I think we'll wrap it up there, Dan. Thanks
Thanks.
again for the presentation, and thanks everyone for sticking around, and we'll see you next week for part 2.
Okay, thanks, Dave.